Welcome to the sixth session of Computational Fluid Dynamics with MR-CFD. In this session, we will simulate the flow inside a cavity using the schemes and methods we discussed earlier. This session serves as an exercise in applying different discretization schemes. In this session, we are going to numerically solve the flow inside a cavity using the simple algorithm. The boundaries of the cavity will be a wall on the left, right, and bottom sides, and there will be a constant velocity u at the top side of the cavity. The dimensions of this cavity along the x and y axes will be denoted as Lx and Ly, respectively. The cavity will be divided into grid cells along both the x and y directions. After mesh generation, delta x and delta y can be calculated. The fluid inside the cavity is assumed to be water with a density of 1,000 kilograms per cubic meter and a viscosity of 0.001 pascal second. As mentioned, the pressure-velocity coupling method we will implement in the code is a simple, semi-implicit method for pressure-linked equations algorithm. For pressure and momentum discretization, we will use a central differencing scheme of second-order accuracy. Let's start with the Navier-Stokes equations to understand the governing equations for this flow problem. Here we discuss the x-momentum equation for two-dimensional flow. The 2D momentum equation in the x direction can be expressed as follows. In our scenario, we are considering the steady-state velocity field for a 2D flow, meaning the time derivative, transient term, of equation is 0. We then focus on the effects of viscosity. Since the fluid is incompressible and has a constant viscosity, denoted by mu, this viscosity term can be factored out of the divergence expression. The viscosity term takes the form of mu multiplied by the second derivative of u with respect to x plus the second derivative of u with respect to y. Next, we assume that body forces like gravity are negligible. With a constant density, labeled as ρ, we integrate the equation across a control volume. The term with ρ becomes a common factor when integrating the square of u times the differential area, dA. We also consider the integral over the control volume of the velocity components uv dot product with the differential area vector, dA. On the other side of the equation, we have the partial derivative of pressure with respect to x multiplied by the control volume plus mu times the integral of the second derivatives of u in both the x and y directions. On the left-hand side, we assume the control volume has dimensions delta y and delta x. The convective term in the x direction becomes a common factor involving ρ multiplied by u at position E times u at position E minus u at position W times u at position W, all multiplied by delta y. The control surface area in the x direction of each cell is delta y. Consider terms like uv at north and south faces. Subtract the south face from the north face and multiply by delta x. We can express the pressure gradient term as the difference between P at positions I plus 1 and I divided by delta x. The volume of each cell is delta x times delta y. Here, delta x cancels out in our calculation. Now, the first derivative of u with respect to x at the east face is equal to u at the I plus 1 cell minus u at the I cell divided by delta x. Similarly, we compute the first derivative of u with respect to x at the west face. This is equal to u at the I cell minus u at the I minus 1 cell divided by delta x. Okay, the second derivative of u with respect to x can be approximated as the first derivative of u with respect to x at the east face minus the first derivative of u with respect to x at the west face, all divided by delta x. When we incorporate these relations, the expression becomes u at index I minus 1 minus 2 times u at index 1 plus u at index I plus 1, all divided by delta x squared. If we multiply this value by the cell volume, delta x times delta y, the delta x terms cancel out in the numerator and denominator. For the discretization of the viscous terms, we can express this as u at index I minus 1 times delta y over delta x, minus 2 times of u at index I times delta y over delta x, plus u at index I plus 1 times delta y over delta x. For the second term of viscosity, we write u at index j minus 1 times delta x over delta y, minus 2 times u at index I and j times delta x over delta y, plus u at index j plus 1 times delta x over delta y. On the left-hand side, the velocity u at the east face, ue, can be expressed as the average of u at indices I and I plus 1. Similarly, u at the west face, uw, is the average of u at indices I and I minus 1. To express the equation in the format used by the simple algorithm as discussed in earlier sessions, we need to gather the coefficients of u sub I, j together. The coefficient of u at the east face, by considering one of ue constant, is ue times delta y over 2. Another coefficient from second term of left-hand side, by considering one of uw constant, is negative u sub w times delta y over 2. The north face velocity, v sub n, can be expressed as the average of v at indices j and j plus 1. The coefficient associated with u at index I and j includes a term of v sub n times delta x over 2. Normal area of y direction is delta x not delta y, minus v sub s times delta x over 2. On the right-hand side, another u sub I term appears, leading to a term 2 times delta y over delta x. Also, there is a mu over rho term as a factor. When we divide the entire equation by rho, the last coefficient for u sub I, j, becomes 2 times delta x over delta y multiplied by mu over rho. On the right-hand side, for neighboring cell values like u at index I plus 1, j must add. The first coefficient is minus delta y over 2 times ue plus mu over rho times delta y over delta x. The coefficient for u at index I minus 1, j is delta y over 2 times uw plus mu over rho times delta x over delta y. For the neighboring values of u at index j minus 1 and u at index j plus 1, we also have corresponding terms. The last term involves the pressure, specifically P at index I plus 1, j minus P at index I, j times delta y. Recalling the formulation in the simple algorithm, these coefficients are named using specific labels. Where the coefficient of u at index I, j is typically referred to as a lowercase e. Each surrounding term has similar notation, with coefficients capturing interactions among neighboring cells. Okay, let's review the simulation for the flow inside the cavity using the simple algorithm in the MATLAB software environment. At the start, The number of grid points in the x and y directions is specified with nx and ny respectively, as well as the length and height of the cavity, which dom-x and dom-y are length of geometry along the x and y coordinates. Then delta x and delta y are calculated, determining the spacing of each cell in the grid. Next, we define the fluid properties. The density is 1,000 kilograms per cubic meter, and the viscosity, represented by mu, is 0.001 Pascal seconds. The velocity, u, at the top of the cavity is set. Under relaxation factors, initially set to 1, are used to stabilize the iteration process. After that, we need to initialize the values and allocate sufficient space for each property related to velocity. This includes arrays for x velocity, updated x velocity u star, and any other variables required in the simulation. Allocating enough space ensures we can store the computed values at each grid cell accurately. And set initial conditions for the velocity at the top of the cavity to 1. In MATLAB, the indexing for arrays typically starts at 1. The index I refers to row numbering. Starting from 1 at the top row and going down to I max at the last row. Similarly, the index j refers to column numbering, starting from the first column labeled as j equals 1 and continuing to j max at the last column. The code for solving the momentum equation includes handling the error calculation that calculate the residual at each iteration, with iteration tracking to determine convergence. The target residual indicates when convergence is achieved. U at the east face is computed as the average of U values at indices ij and ij plus 1. Similarly, U at the west face is the average of U at indices ij and ij minus 1. For the north and south faces, the values are calculated at indices I minus 1 and I plus 1 respectively. Values U at each face represent the average of values at neighboring cells, such as V sub n being the average of values at indices I minus 1, j and ij. Coefficients for each neighboring cell, such as a sub e, a sub w, a sub n, and a sub s, are calculated based on expressions defined earlier. In the x momentum equation, a sub e is the coefficient related to u at indices ij, while a sub p corresponds to the pressure term, which involves a minus delta y factor. By dividing all terms by the coefficient of u at index 1j, we define the coefficient d for the simple algorithm. We update the velocities for each iteration using these coefficients to find u star, which is an intermediate velocity. As for boundary conditions, u at the top boundary is set to 1, while u at the other boundaries, which are walls, is assumed to be 0. In the same way, we can calculate the y momentum equation. For instance, u at the east face can be calculated as the average of u at neighboring cells. Coefficients for neighboring cell velocities can also be calculated. Variables like dn and v star can easily be obtained. For boundary conditions in this scenario, the v velocity at all boundary cells is set to 0. Moving on to the pressure correction step, we use the continuity equation. The initial value for the pressure correction, or P prime, is defined as 0. The continuity equation is represented as the partial derivative of density with respect to time plus the divergence of rho times v. Considering steady state and incompressible flow, we simplify and integrate to reach an equation where u at the east face minus u at the west face plus v at the north face minus v at the south face equals 0. Using the simple algorithm, we replace u at the east face with u star at the east face plus dE times the pressure difference between cells I plus 1 and I. Similarly, for the west face, u can be replaced with u star at the west face plus dE times the pressure difference between cells I and I minus 1. For v at the north face, it can be replaced with v prime n plus dn times the pressure difference between j plus 1 and j minus u star at the south face, and dn times the pressure difference between j and j minus 1. This results in an equation equals 0. Coefficients for pressure correction at the east, west, north, and south cells are calculated. From this, the pressure correction at cell ij can be calculated, namely P prime, as defined in the simple algorithm. In this context, Bij is the summation of u star and v star at the east, west, north, and south faces, which are all known in this section. The coefficients for the pressure at I plus 1 involve dE multiplied by delta y, representing the normal area in the x direction. Similarly, the coefficients AE, AW, AN, and AS are calculated. The coefficient AP, representing the pressure coefficient of cell ij, can also be calculated. By substituting all these values into the final equation, the pressure correction at cell ij can be determined. Next, we correct the pressure, where the new pressure P is equal to the old pressure plus alpha times the pressure correction. The under-relaxation factor, alpha, is important for ensuring stability at the start of the simulation. For velocities, u star and v star are corrected according to the algorithm, considering boundary conditions. The residuals are calculated by summing all values of mass imbalance, B sub ij, across all cells. At final result, if corrections became zero, the continuity equation changed to B is equal to 0. Plotting the residual every 100 iterations helps in visualizing convergence. Then, the updated values of u, v, and p are fed back into the loop to continue the iterations until convergence is achieved. The following visualization steps display the results, including the visual error versus the number of iterations. Afterward, the velocity vectors within the cavity are shown, along with the contour plots of u velocity. You can adjust u at the top boundary and rerun the simulation to observe changes in the velocity vectors and u velocity contours. Initial parameters like the number of grid points and domain dimensions can be modified. Now let's explore the effect of under-relaxation factors. Initially, we run the simulation with relaxation factors for flow and pressure set to unity using a grid size of 51 by 51 in the x and y directions. After running the simulation, convergence is achieved in 3,500 iterations. Next, we reduce the under-relaxation factors to 0.4 and rerun the simulation. This time, convergence is reached in 5,000 iterations. The reason is that with each iteration, only 40% of the corrections are applied to the velocity and pressure. While this increases the stability of the simulation, it also increases the number of iterations required for convergence. By altering the dimensions of the cavity geometry, such as increasing its length and depth, you can run the code to obtain results for various cavity types. This allows you to observe the flow patterns within the cavity. In a cavity with greater depth and shorter length, you'll notice that the effect of the velocity at the top of the cavity does not easily diffuse to the bottom. Also, the u velocity for each of these scenarios presented here. Additionally, by altering the boundary conditions, we can solve for flow patterns under different properties. For example, consider a scenario where the velocity at both the top and bottom sides of the geometry is set to 2 meters per second in the same direction. In this case, two vortices may form, rotating in opposite directions, located within the top and bottom sections of the domain. This setup can illustrate complex flow interactions and highlight how boundary conditions significantly affect the internal flow dynamics. The rotating vortices demonstrate how flow velocity and direction at the boundaries can influence the formation of distinct flow structures, which is crucial for understanding fluid behavior in various engineering and scientific applications. As the final scenario, consider setting equal velocities for the top and bottom sides of this domain, but in opposite directions. In this case, vortices that rotate in the same direction can appear. In some situations, these two vortices may combine and generate a larger vortex in the center of the geometry. At the top side, the u velocity is aligned with the upper boundary, and at the bottom side, the u velocity aligns with the bottom boundary velocity. In this video, we used a MATLAB code to solve the flow inside a cavity using the simple algorithm with a central second-order discretization scheme, as discussed earlier. The goal of this course is not to focus on coding or coding fundamentals. This code serves as an example of how these relations can be interpreted into code. For those interested in coding, this is a basic example, and you can try adding modifications to develop even more complex algorithms, like simple C and further corrections. You might explore generating the PISO algorithm. For those not interested in coding, this video assures you that the topics we discuss involve the same algorithms used in Fluent software, and they are effective. In our next session, which will be the final one, we will focus on Fluent itself and review the materials we learned in this session. The most important aspect for those aspiring to be applied CFD engineers is understanding how this information can help. In the last session, we will review what we should at least know when we use ANSYS Fluent.